Please interrupt. Just because of the lag, it might take me a second to hear your question, but I'll do my best. Thanks for the great introduction. I'm Ryan Marcus. I'm currently a postdoc at MIT. I also do some work with Intel Labs. Today I want to talk about how machine learning can improve query optimization, or if machine learning can improve query optimization. Sometimes it doesn't work so well. You can get a copy of these slides at the URL that's on the screen, ryan.cab/Athens20, and I'll have that link up again at the end in case you miss it. Cool. So I know that you all generally know a bit about databases and query optimizations, but just to give a little background or a refresher, the main purpose of a query optimizer is to transform a SQL statement into a query plan, right? So you get something like select star from, and then a bunch of tables, then a where clause, maybe a group by, maybe an order by, lots of possible complexity. And then the query optimizer is responsible for turning that into sort of a program, right? A query plan tree, pick a join ordering, select operators, that kind of thing. These are huge, massive efforts. So in Postgres, possibly the most sophisticated open source database, or at least the most mature, there's 42,000 lines of code just in the query optimizer. In SQL Server, the Microsoft product that is arguably one of the best databases out there, there's over 1 million lines of code just in the query optimizer. Oracle, when I asked them, wouldn't tell me how many lines of code was in their query optimizer, but they would tell me that they have 45 to 55 full-time employees, or FTEs, working on their query optimizer every year. So assuming those people are getting paid at market rate, Oracle spends about $5 million a year on their query optimizer, at least. So they're huge, massive efforts with a lot of complexity. And in addition to being huge and expensive and complicated, they also don't work super well out of the box. These query optimizers generally require tuning on a database level, meaning that you as the DBA or the database user have to tweak the optimizer in some way. And across all three of these systems, you can get somewhere between, around a 15 to 25% improvement from doing that per optimizer tuning. So you don't have to do it, but if you do, you get big gains. So all I'm trying to say here is query optimizers, they're really expensive to maintain, and they already don't work perfectly. So there's lots of room for improvement. The classic query optimization architecture looks something like this. You generally have 3 modules: a cardinality estimation module, a cost model, and some kind of dynamic programming search. So the cardinality estimation module is responsible for doing things like estimating the size of intermediary results. If you're joining tables A, B, C, and D together, the cardinality estimator will decide, okay, how big is AB, how big is BC, that kind of thing. The cost model is responsible for mapping a candidate plan or a partial candidate plan to some kind of cost, right? Saying, I think this will be this expensive to compute, and things with lower cost are more desirable. And finally, your dynamic programming search method is generally some kind of either Sellinger's algorithm, dynamic programming search to solve this NP-hard problem. So today in modern databases, cardinality estimation is normally done either very naively with something like the uniformity assumption, or slightly more sophisticated techniques like histograms or most frequent value, or MFVs. Cost models are generally pretty simplistic. They tend to be polynomials. A nested loop join is quadratic, a hash join is linear with some hand-tuned coefficients. So that's sort of why these things have why query optimizers have such large complexity, because they fit into these 3 modules, each of which carries a lot of weight. So one of the most obvious places to try to apply machine learning to query optimization is in cardinality estimation, right? They're just estimates, so if the model has errors, it's not necessarily a problem, and it's a very kind of natural mapping onto supervised learning, right? You have some training data. I know if I join A and B with this predicate, I'll get this many rows out, and it seems natural to try to learn a function to do better cardinality estimation. The problem with applying machine learning directly to cardinality estimation is you don't always get the results that you're expecting. So consider a very simple query like the one here, where we're joining 3 tables A, B, and C together. So our join graph looks like this. It's a simple line. We're joining A with B, and we're joining A with C. There's a couple possible plans, but consider these 2, right? So one possible plan is that I join A, B together first, and then I join the results with C. That's shown on the left. Another possible plan is that I join A and C together first, and then I join that result with B. Right? There are other plans, but they have cross joins, so we'll ignore them. So the purpose of cardinality estimation is going to help us differentiate which one of these two plans is better, right? So let's say that the true actual cardinalities are these given here. So if I join A and B, that's going to give me 8 tuples. And if I join A and C, that's going to give me 15 tuples. So with those true cardinalities, I know, okay, I'm going to want to join A and B first, right? It's going to, with assuming a simple cost model, I want to do the smaller join first. Now, suppose I have an estimator. We'll call it estimator 1. And estimator 1 predicts that the size of A join B will be 4 tuples, and the size of A join C will be 9 tuples. So, it has some error, right? It guessed 4 instead of 8. It guessed 9 instead of 15. So we can quantify this error using a standard machine learning error function called the L2 loss. L2 loss is just a fancy word for mean squared error. So you take the difference of every element, you square them, you add them up, and then you take an average. So here we say, okay, our error on the first estimate was 4, our error on the second estimate was 6, so our total error is 4 squared plus 6 squared. Using this estimator, we still pick the correct plan. We still pick the plan that joins A and B first and then joins the result with C. Now, suppose I had a second estimator, right? And this estimator guesses 12 for A join B and guesses 11 for A join C. If we do this, our estimator has a lower error, right? In the first estimate, it's only off by 4, which is the same as the previous estimator. And in the second estimate, it's also only off by 4 as opposed to being off by 6. So the L2 error of the second estimator is lower than the L2 error of the first estimator. However, if we do query optimization based on the second estimator, we're going to pick the suboptimal query plan with respect to the true cardinalities. We're going to choose the plan that joins A and C first because we predict A join C to have a lower cardinality than A join B. So even though the error of the estimator is lower, we got a worse plan. So it is totally possible with a cardinality estimator that a cardinality estimator with higher error is going to give you a better plan. So the takeaway here is can we use machine learning to predict these cardinalities? Well, we can, but we should expect it to have a limited impact on query optimization because just decreasing that error score, just decreasing the distance from the correct answer doesn't necessarily lead you to actual query plans. So in order to test this hypothesis, we evaluated 3 state-of-the-art learned cardinality estimators. One of these came from our lab. So we made this mistake before we realized it was a problem, the MSCN. And we looked at them in terms of their relative L2 scores to the Postgres estimator and their relative query latencies to the Postgres query optimizer. So the way to read this chart is that the MSCN technique, which stands for multi-set convolutional neural network, had a relative L2 score of almost 0.1. So if the Postgres L2 score was 1, then this was almost 90% lower than the Postgres score. So the estimates are way closer to the true value, right? Way closer. But the actual query latency only improved by 1 or maybe 2%. So way better estimates, only slightly better query plans. We also looked at local models, which were presented at the AIDM workshop last year. This had slightly higher relative L2 scores, only about 20% of Postgres' error, and actually made query plans worse. The same is true for the Naru system that came out in SIGMOD 2020. So you can use machine learning to improve cardinality estimation, but you do so at your own peril because you may get better estimates. You may see, oh man, my estimates are 2 times better than Postgres. They're 3 times better than Postgres, but your actual query latency might not improve at all. So
Ryan,
motivated
can I
by
ask
this.
a question here?
Yes.
So if you go back to the slide that you were just showing, just as as a visual hint. So what you're saying here implies that the formulas that we have for cardinality estimation are already doing a great job, but this is not always the reality, right?
Right. So I guess what I'm trying to say is that the quality of a cardinality estimate is hard to verify. So we know for sure that Postgres will just be orders of magnitude wrong, right? After just a couple joins, you can do like a 4 or 5 level join, and the Postgres estimates will start to be off by 100x, 1000x, you know. But just bringing down the raw error, just bringing down the pure percentage difference between your estimates and the actual targets doesn't necessarily give you better query plans.
I get it.
So because of that, we started to ask the question of, yes, okay, we could do cardinality estimation for query optimization, but when we do so, we don't necessarily see the huge, even though we see huge improvements in estimation quality, we don't see huge improvements in query plans. So maybe there is another approach that we can use. So the next thing that we investigated was this idea of doing end-to-end query optimization in a learned way. So what this means is, instead of just looking at one module, instead of just looking at the cardinality estimation module or the cost modeling module or the dynamic programming search module, we're going to look at the whole system together and see if we can apply one machine learning algorithm to learn all 3 of those components simultaneously. So obviously it's much harder and it requires a little bit of background. So I want to start with some background and some misconceptions that database people often have about the machine learning community, and that the machine learning community often has about the database community. So we know from, machine learning is happening, right? Like 5 years ago, it was a little uncertain, but today we're all very sure that machine learning is going to be a part of the world for at least the next couple coming years. And the database community has had an interesting time adapting to those changes. So there's 2 general conceptions of machine learning that are wrong, and the database community has mostly gotten over these, but I'm going to talk about them anyway. So one idea of deep learning is that it's this black box, right? It's this totally uninspectable thing that just so happens to work in a couple of cases, and it's going to fail and fall over and be horrible at a moment's notice because we can't actually investigate anything about it. And there's this other view of deep learning that it's just magic, right? It's just, oh yeah, it just works all the time. It's absolutely perfect. It does image classification great. And obviously both of these views are very, very wrong. So I wanted to spend a little bit of time talking about what makes deep learning good, what makes it work, and how can we build sort of an intuitive understanding for what's happening inside of deep learning methods. So within the machine learning community, there's been a whole lot of work done trying to apply deep learning for query optimization. There's been some reinforcement learning-based approaches, which we're going to talk about next, and there's been some cardinality-based approaches that we've already discussed. All of these approaches sort of take, including stuff from prior work from myself, take this approach where you kind of just add deep learning and stir. They view deep learning as this black box. And when doing that, they make 5 kind of mistakes that I want to highlight. And so these are sort of sniff smell tests that you can use if you're reading a paper about deep learning for query optimization. If they do one of these things, then there's probably something wrong. So the first one is using fully connected neural networks. Fully connected neural networks, they're the first kind of neural network that you learn about. They're very simple. They have some nice theoretical properties, but in the real world, they are almost never the right thing to do. And we'll go much more into detail on this next. The second thing that often pops up in these papers is train/test set leakage. So, in machine learning, you normally take a part of your data and you use it for training, and then you take a part of your data and you use it for testing. And after you train your model on the training set, you evaluate it or validate it on the test set to try to make sure that you actually learned something that can generalize, right? But frequently, when database researchers aren't as careful as they should be, again, myself included, you might find that the differences between the train and the test set are very, very similar, right? Like maybe in the training test set, you have a query with the predicate that looks for all movies made after 2005, and in the test set, you have one that looks for all movies made after 2006. So almost an identical query that appears in both sides. A third signal is off-the-shelf reinforcement learning algorithms or simple regression loss functions, right? So we just showed an example in cardinality estimation where if you just try to minimize the L2 error, you can easily get estimators that seem like they're way more accurate, but don't actually improve your query performance at all. The fourth sign is that there's little to no integration with a broader database, right? So if you just, a lot of papers like the rejoin paper that Olga and I worked on at the end of my PhD, we said, here's a join order enumerator. We have no idea how to stick it into an actual database, but here it is. Bad sign. And the final sign is that there's no evaluation of actual query performance. So I've started referring to these things as the 5 deadly sins of machine learning for databases. They happen a lot. We as a community are getting better at it, but you should keep these things in mind when you're evaluating work, because each one of them is sufficient to really make a system's not practical, right? So today, next I want to really focus on fully connected neural networks, because this is where a lot of the black box understanding of deep learning comes from. So if we look at what makes deep learning good, what makes deep learning successful, we can see that it's really mostly been in 2 application domains. The first one is computer vision, right? GANs, classification networks, all that kind of stuff. They've been phenomenal. They blew the non-deep learning stuff out of the water. It's been huge. And the second one is natural language processing. Both of these fields saw huge, gigantic advancements when deep learning came around, and they're clearly the 2 biggest deep learning success stories. So if we look at the kind of neural networks that they use in those 2 domains, we almost never see a fully connected neural network. Instead, what we see is in the realm of computer vision, we see a thing called a convolutional neural network. And a convolutional neural network works by basically having a filter bank, a stack of tiny little sliding windows that you move across an image in order to transform that image into another image. And you do that a whole bunch of times. In natural language processing, the most common architecture that we see is this thing called long short-term memory networks, or LSTM networks. A little more complicated. I'm not going to try to describe them intuitively, but essentially they're a neural network designed for processing sequences. So the story here, what happened was that in order to build a neural network that recognized objects and images, we modeled the low-level structure that were used by the human eye. So the convolutional neural network wasn't just something that was made up, right? We looked at how the human eye worked. We saw that the human eye did this sort of sliding window thing. And then we said, okay, can we model a computer? Can we make a computer model that exact process, right? Similarly, in natural language processing, when we wanted to build a neural network to recognize words and speech, we looked at the low-level structure that was used by the human part of the brain that does that, which is the prefrontal cortex, and that, a combination of neuroscience and computer science led to this LSTM model. So yeah, I know this is a little hand-wavy, but the point that I want to drive across is that the biggest deep learning success stories have always followed the same pattern, which is to build a neural network to do some specific task. We've modeled a low-level structure used by some expert system that we know works well. So this in the machine learning community is known as inductive bias. When you model your network architecture itself against something that looks a whole lot like an expert system for solving your problem. You're biasing the model towards learning functions that are more like that expert system. So if I design my neural network to do similar computation to an eyeball, then I biased my neural network to learn functions that are more like eyeballs. So this basic idea is not something that we as systems people love, right? As systems researcher, we don't want these complex problem-specific solutions, right? We don't want to have to think about like, okay, I need to use this neural network for this task, and this neural network for this task, and this neural network for this other task. What we want to do is we want to throw out all of that complexity, and we want to generalize, right? We want to figure out what's the relational algebra of neural networks. So our first response to seeing the success of convolutional neural networks and long short-term memory neural networks might be, can't we be more general, right? And if you look at the neural network literature, you might think, oh yeah, we totally can't, right? The famous theoretical result about fully connected neural networks is that they can represent any arbitrary function. The problem, of course, is that you don't want an arbitrary function. So consider a very simple example where we're trying to learn a function that will predict ice cream sales based on temperature. So the data shown in the bottom left there, and we can see there's kind of like a correlation: hotter days, more ice cream sales. So I could potentially fit 2 different arbitrary functions to this data, right? I could fit arbitrary function A, or I could fit arbitrary function B. I think it's pretty clear which one of these is a better model of the underlying data, right? arbitrary function A, it goes off into space. It's weird. It's not monotonic, whereas arbitrary function B seems like a reasonable representation of the underlying trend. The difference between these two models is inductive bias. So we don't want that arbitrary function. We don't want that generalizable thing that can do everything. We actually want, in order to find a function that generalizes, we need to architect the network in such a way that it's biased towards learning a function that actually makes sense for our application, right? We're not just interested in an arbitrary mapping that happens to get our training data right. We're interested in a mapping that when we apply it to new data will make sense. So in old school machine learning, the way that we accomplished this was regularization. We would, penalize the weights of the model, or we would force a maximum polynomial degree, or limit the depth of a random forest, or something like that. In deep learning, we don't have these regularizations so easily available. In deep learning, we basically just use stochastic gradient descent. So if we're just using stochastic gradient descent, how do we know if our functions will generalize? And the answer is inductive bias, right? One way to do it is to model it after some kind of expert system that we know generalizes. So to put it formally, what you want to do in order to make deep learning work really well is constrain the type of function that you're using based on the prior knowledge of the problem at hand. If you know you're going to observe a linear relationship, fit a linear model. If you know you're looking at visual data, model the human eye. If you know you're going to be processing parts of speech, model the part of the brain that does that, right? The closer that you can get the form of your function to match something reasonable, the more success you're going to have out of deep learning. So to drive this point home a little bit, if we think about MNIST, which is a popular machine learning task, which its job is to classify digits. So for example, in those 5 images on the bottom of the screen there, the goal of the machine learning algorithm is to select the correct class for each image. In this case, that would be a 5, and then a 0, and then a 4, and then a 1, and then a 9. So if I train 3 different machine learning algorithms in order to solve this problem, a fully connected neural network, a convolutional neural network, and a random forest, and I evaluate them all on these on this task, what I'll see is that the convolutional neural network, which is modeled after the human eye, and human eyes are pretty good at recognizing numbers, I get almost a 98% accuracy. That's basically perfect. That's pretty much as good as a human. What might be surprising is that the random forest, the old school machine learning random forest, actually does a better job at this task at 92% accuracy than a fully connected neural network. And the reason for that is because of inductive bias. The convolutional neural network wins because its function is of the form that is going to be really good at recognizing images. And the fully connected neural network loses out because its inductive bias is really not great at recognizing images. So here's sort of the machine learning details of what's going on, which I'm going to go over very quickly here so we can get back to talking about databases. But the idea is your convolutional neural network has a strong inductive bias from the visual system. Random forests also have an inductive bias. That inductive bias is normally called conditional sparsity. The idea is that if one tree in your random forest splits on a particular pixel, then it's much less likely that the next level of that tree will split on a similar pixel because pixels in a local neighborhood are correlated. And of course, fully connected neural networks also have an inductive bias. The inductive bias of a fully connected neural network is that every input feature, in this case a pixel, should get a weight no matter what. This bias is used towards what mathematicians would call a sensitive or simple function. So again, if that didn't make any sense to you, it's okay. The only takeaway I want to get across here is that deep learning is fantastic if and only if the inductive bias of the model matches reality. If the form of the function that you're going to fit makes sense for your problem domain. So all of the deep learning hype, the idea that you can learn things end to end, the idea that automatic feature engineering can happen, the idea that you can get super great generalization, all of this can be a reality, but you have to get the model architecture right. This sort of begs the question, well, okay, what about database systems, right? Convolutional neural networks are to computer vision as what is to database systems. So obviously I don't have the answer, but I do have a proposal, and it's a proposal that we've tested quite a bit, and it's this idea called tree convolution. I'm going to do a slight cliffhanger there, but I promise I will get back to it. So I want to talk about NEO, which is our learned query optimizer. This is an end-to-end system, so it's not just about cardinality estimation. NEO is about trying to learn all three of those modules at once. So we're not going to use an explicit cost model, we're not going to use an explicit cardinality estimator, and we're not going to use an explicit dynamic programming search. We're going to try to learn all of that stuff from the start at the very beginning. And the point of NEO is to demonstrate an early prototype of what a deep learning powered optimizer might look like. We did integrate it into a broader database, but it still has some problems that prevent it from being super possible. One of the main features of NEO is that it automatically tunes itself per database. So unlike like the Postgres or the Oracle optimizer, you don't have to, that tuning happens automatically. And our sort of headline result is that NEO can match or exceed the performance of Oracle or SQL Server, those state-of-the-art query optimizers, with just about 24 hours of training. So how is that possible? The basic idea behind NEO is shown in this diagram. First, we observe how a simple query optimizer, like a textbook, Selinger, left-deep, Boneling kind of thing, handles a sample workload. So we observe how that optimizer works for just a little bit on a small sample workload. Then we train a combination of a value model and a planned search module to emulate that expert. So we watched how that simple query optimizer worked, and then we initially trained two components, a value model and a planned search, in order to emulate it. I'll go into more detail, of course. And then once we've trained our model to emulate this expert, we create a feedback loop where we refine those two modules, the value module and the planned search module, using real query latencies on user-submitted queries. So the high-level overview is, first, we take a sample workload and we do a little bit of pre-training in order to get our model to do something slightly reasonable. And then as a user query comes in, we process that user query, we observe its actual real-world latency, and then we adjust our models accordingly. So the first problem that NEO has to solve is how to represent query optimization as a reinforcement learning problem or a Markov decision process. So I'll talk about that first, and then I'll talk about the design principles of NEO. So the biggest design principle of NEO is, of course, finding the right inductive bias. We say we shouldn't use a fully connected neural network, and we propose this idea of tree convolution instead. We also design NEO around this idea of learning from demonstration, which is this watching how a simple optimizer works first. Today, I'm only going to have time to give an overview of that. And the final design principle around NEO is this idea of learning embeddings, neural embeddings that are a lot like word vectors instead of using histograms or exceptions list. Unfortunately, I won't be able to talk about that today, but you can find more details in the paper. So before talking about how we model query optimization as an MDP, I want to just lay out some of the assumptions that we're going to make. The first assumption we're going to make about each database is that query plan trees are binary. And so what I mean by that is that every operator has two children, one or no children. So like every internal node is a join and every leaf node is a scan of some kind. The second assumption we're going to make is that these query plans are not distributed, that they're all being ran on a single machine, a single node. The third assumption we're going to make is that there are a fixed number of join operators. And by a fixed number of join operators, what I mean is that there's like, hash join, merge join, loop join. That's 3. A query plan can have as many joins as it wants, but we're going to assume there's a fixed number of ways that we're going to process those joins, a fixed number of strategies to do joining. And the fourth assumption that we're going to make, and I know this is a big one, is that everything is only an equijoin. So like no theta joins or complex joins like that, just this column of this table equals this column of that table. So the way that it works is you can think about a Markov decision process as sort of a graph. And in that graph, you have states, actions, and rewards. And so a state sort of represents like your current view of the world, and the actions represent the things that you can do in that world that will take you to a new state. So for example, if I'm trying to come up with a query plan for the relational algebra statement at the bottom here, a 5-way join of these tables, initially I can think of my world as starting out with I've made no decisions at all. I just have R1 through R5, and I'm trying to decide how to build a plan. So one thing that I could potentially do, one action that I have from this initial state of the world, is that I could decide, okay, I'm going to combine R1 and R2 together with a hash join. So if I select that action and I take it, I move into a new state. And in this new state, now instead of having 5 relations to choose from, I only have 4 relations to choose from. I have R1, which represents this intermediary result, right? This hash join of actor and appears in. And then I have R2, R3, and R4. So now my action set is a little more limited, right? But for example, now I can choose, okay, I'm going to combine R2 and R3 using a sort merge join. If I select that action, then I create another intermediary, and I move into a new state. In this state, and so on and so forth until you've built an entire query plan tree. Eventually, you reach a state where there are no more actions available to you. You have a complete query plan tree. There's nothing else to do. And so at this point, you execute your query plan. You execute the thing that you created. Generally, in a Markov decision process, the goal is to maximize some kind of reward. So we say that the reward is just the negative latency. It's not a super important detail. You can just think about maximizing or minimizing or however you want to think about it. So this view of query optimization as an MDP isn't super useful on its own. It only becomes useful because now that we have cast the problem as an MDP, we can start to think about how we would apply deep reinforcement learning to these tasks. So the way deep reinforcement learning works is actually pretty close to how traditional query optimization works. So for example, here's a high-level view of that MDP I just showed you. So here initially we start out with 3 tables unjoined, A, B, and C. And then I have a set of possible actions. I could join AB first, I could join BC first, or I could join AC first. And then from there I have other actions. The red circles that I put at the end represent the latencies of the resulting query plan. So for example, if I choose the middle action to join BC first, and then I choose the top action, which is to join A on the right, that results in a query latency of 9 seconds. Whereas if I had made other decisions, maybe I could have achieved a query latency of 3 seconds. Now, if you're a traditional query optimizer, what you want to do is you want to use a cardinality estimator and a cost model to come up with some kind of cost function, C, that's going to estimate sort of the intermediary costs of each one of these plans, right? So I could have a cost model that estimates, okay, my initial decision to join just A and B together, that has a cost of 1. My initial, if I instead made the initial decision to join BC together, that would have a cost of 2, etc. And then the idea is that your cost model on the final query plan would tell you the correct latency, right? Or tell you the correct cost of the plan. So when you have a cost function like this, you have to use some kind of dynamic programming approach in order to figure out where your optimal plan is, right? So if you start at that initial node, you have to do a search to, expand different nodes and do the Selinger 2 to the n thing in order to figure out that, okay, I want the plan that joins BC first and then joins A on the left. So the way that deep reinforcement learning works is deep reinforcement learning says, okay, forget about that cost function. Forget about estimating the intermediary cost of a plan. Instead, what we want to do is we want to pretend that we have this magical oracle function, this magical thing called Q, which maps each state, each intermediary state, to the best possible latency achievable from that state. So what this means is that when I run my Q function on all of my nodes, I'm going to get the latency of the best possible plan I could get to from that node. So for ABC, my initial state, my Q value is 3, because the best possible query plan that I could reach from that initial state has a latency of 3. Now, if I were to choose to join AB together first, the top action, then my Q value would be 5. Because once I've committed to that action, once I've committed to joining A and B together, the best possible query latency that I can achieve is 5. So if I have such a magical Q function, then it's really, really easy to do query optimization, right? I no longer need a dynamic programming search. All I have to do is start at the top of the tree and say, okay, which one of my children has the lowest Q function, lowest Q value? Okay, I pick that one. And you continue that process until you reach the end of the tree. So obviously this begs the question of, well, where do I get this Q function from, right? Where do I get this magical thing from? Because of course there is no Q, right? If we had that, then we'd be done and we wouldn't need to do anything fancy. So the entire idea behind deep reinforcement learning, at least one subfield of it, is to learn an approximation of this Q function called Q hat. So our goal is going to be to learn this magical oracle Q function, or an approximation of it, using machine learning methods. And that's all there is to deep reinforcement learning. So the way that we're going to do this, the way that we're going to learn this magical Q function, is called value iteration. So the idea behind value iteration is that we're going to start out with some initial policy, some initial way of navigating that MTP that's totally random. And it's just going to choose whatever action it wants to choose and go on with its life. Once it does that, we're going to run that policy on a query plan. And that query plan is we're going to execute it, and we're going to observe some latency from it. From that latency, we're going to assume that our initial policy, our pi0, was optimal, and we're going to train a Q approximator in order to match that policy. Then we're going to repeat this process. Then it's like, okay, we have a new approximator, so I'm going to use that as my new policy. And I'm going to keep going and iterating over and over and over again. Doing value iteration in this way has some nice theoretical proofs, some nice properties that I'm not going to get into today. But the general, it's a generally accepted, it's a good way to model that oracle function. So this begs the question of how do we approximate that Q function? So one thing that we could do is we could take all of our states, our ABC or our A join B, comma C, and we could flatten it into some kind of single vector, and then we could feed it into a fully connected neural network. That's not really how deep learning became successful. That's not really the how things work, right? What we really want to do is we want to find the right inductive bias. We want to find the neural network architecture that can look at a partial query plan and intuitively determine, okay, what's the best I could possibly do from this state? So our idea for how that works is tree convolution. So the idea that motivated tree convolution was when we were looking at query plans, we tried to ask ourselves, what do we look for as humans, as database experts, to try to determine whether or not a query plan is going to be good or bad? So if I showed you this query plan here on the right, you might notice, oh, okay, you have a whole bunch of stacked sort merge join operators. This could be good because it might avoid a resort, right? You might get a very nice pipelined merge plan going all the way up the tree, possibly. Now, if I showed you this plan instead, you might say, oh, you have a hash join on top of a sort join, on top of a hash join, on top of a sort join. You're definitely either going to have to rehash in between each one of those join operators, or you're going to have to resort. There is no avoiding it. So this is probably not going to be good. If you're a DBA and you have some familiarity with this database, you might know that the appears in relation is pre-sorted on disk, right? Like it's a clustered table sorted on its primary key. And therefore, it should probably be going into a sort join instead of a hash join. So that might also give you an indication that this query plan is maybe not great. What's common about all of these observations is that we examined local structure first, and then we built those local structures into higher level features. So for example, we saw a sort on top of a hash, and then we saw a hash on top of a sort, and we saw a sort on top of a hash. We saw all those local features, and then we said, this is a chain. This is a gigantic chain of sort hash, sort hash, sort hash, which we don't like. Or we saw local features like, appears in is going into a hash join. That can't be right. This whole query plan's probably not doing exactly the right thing if it's not taking advantage of the fact that I pre-sorted this relation. So based on those local clues, based on clues from the local structure of the query plan, we built up this bigger idea of what was going on. So how can we encode this into a neural network architecture? Well, similar to image convolution, we borrowed this idea of tree convolution. So imagine that I have the query plan on the left there, a hash join on top of a sort join of A, B, and C, and say that I wanted to come up with a way to detect this local feature of whether or not I had a hash on top of a sort. One way to do that would be with a tree convolution filter. And so there's an example filter in the middle of the screen here, and the way this filter gets applied to the query plan tree is very similar to image convolution. You sort of slide it around. So for example, I line up the filter, I line up the hash box with the top and the sort box with its left child and the zero box with its right child, and then I do a dot product. I say, okay, hash is a hash, so that's 1. Sort is a sort, that's a 1. C is not 0, so that's 0. And my new node becomes a 2. Then I take that filter and I slide it down the tree. I say, okay, now I say, is a sort a hash? No, it's not. Is A a sort? No, it's not. Is B 0? No, it's not. So that's a score of 0. I continue to slide this filter across the entire tree until I built a whole new tree from it. Now, this new tree has the exact same size as the original tree, but it's lit up in one place, right? There's 1, 2, and everywhere else is 0, exactly where this local feature that I care about occurred, right? So right where I had a hash on top of a sort, this new tree has a big number, and everywhere else it has a 0. So this is, in machine learning speak, this is called a feature detector, right? We have built a tiny little filter that we can apply to our whole tree, no matter how big that tree is, that will create a new tree that is lit up exactly where this feature occurred, right? Exactly where this hash on top of a sort happened. I could have another filter as well that looks for the B relation going into a sort merge join. If I applied this filter across my entire tree, I would see, okay, yes, again, the feature is detected only where it actually occurs. So I showed you 2 examples of manual filters, of filters that we, designed ourselves in order to illustrate a point. But there's no reason why you have to make up these filters on your own. Just like in image convolution, these filter weights can be automatically learned. The idea is you represent each one with a parameter that's differentiable, and then you use stochastic gradient descent in order to find a good model. And then you stack them on top of each other in order to learn higher and higher level features. So for example, if I have one filter that looks for a hash on top of a sort, that produces a new tree. I then run that tree through another filter that might look for a stack of 2s, and then I would know, okay, now I have an even longer chain, right? And so I can stack those up, and I can get a fully differentiable function that I can learn with stochastic gradient descent. This tree convolution operation can also be effectively vectorized onto a GPU, which is very convenient because training these neural networks is, an expensive operation. So the way that NEO approximates this Q function is with its value network, and the value network looks like this. We take a plan tree, we run it through 3 layers of tree convolution, and then we do a thing called dynamic pooling, which is basically just a way to flatten out all of those trees into a single vector. We run it through one fully connected layer, and we use that to get a cost prediction. Okay. I saw something show up in chat. If you have a question, feel free to just shout it out. Okay. So that's how we approximate the Q function. And by approximating that Q function, query optimization becomes really easy. We just follow that Q function until we get to a full query plan, and we should have a pretty good estimate. One of the problems with value iteration is a little surprising and is very different from other deep reinforcement learning problems. So deep reinforcement learning is very sample inefficient. And what sample inefficiency means is that you have to run the network, you have to play the game for a very, very long time before you get good at playing the game. The problem is if you're bad at query optimization, you're not going to be able to execute as many queries in the same amount of time because doing worse takes longer. So imagine that you're playing Pac-Man or Mario or really any video game. If you're really bad at Pac-Man, you're going to die really fast. And when you die really fast, you're going to get that signal back quickly, right? Like, oh, okay, I probably shouldn't run into the ghosts. I probably shouldn't fall off the edge, right? But in query optimization, if you make a really bad query plan, you're going to have to wait a long time for that query plan to finish before you know that you did a bad job. So this is so just to quantify how bad that could be, here's a histogram of every possible query plan for example query over the IMDb data and its latency. It's borrowed from the How Good Are Query Optimizers Anyway paper. So What this histogram shows is that some query plans for this query can execute in just 1 second. Other query plans, really, really bad query plans, might take an entire year to execute. So if you start out with a random policy, if you start out doing query optimization, just picking randomly, odds are you're going to end on a query plan that takes between 10 hours and 4 days, right? The mean of this distribution, or the median, sorry. That's not good, right? We want to be able to train a lot faster than that. We don't want to have to wait, if we need 1,000 queries in order to learn a good policy, we don't want to have to wait 1,000 hours or 4,000 days, right, in order to do that training. Luckily, what this histogram shows is that some query plans for this query can execute in just 1 second. Other query plans, really, really bad query plans, might take an entire year to execute. So if you start out with a random policy, if you start out doing query optimization, just picking randomly, odds are you're going to end on a query plan that takes between 10 hours and 4 days, right? The mean of this distribution, or the median, sorry. That's not good, right? We want to be able to train a lot faster than that. We don't want to have to wait, if we need 1,000 queries in order to learn a good policy, we don't want to have to wait 1,000 hours or 4,000 days, right, in order to do that training. Luckily, though, we actually, we already have query optimizers that can do an okay job, right? We have heuristic query optimizers that have been around forever that can do okay. So, for example, the Selinger algorithm, the simple lefty 2 to the n dynamic programming scheme with uniformity estimators for its cardinality and a simple cost model, achieves that green line, achieves a plan that takes a little more than a minute, about 3 minutes. So if we start from random, our expected execution time is somewhere between 10 hours and 4 days. But if we start from a really, really simple, like just a textbook query optimizer, then our expected time is more like a minute or 10 minutes, much more acceptable. So the idea with Neo is that we used in Neo is that instead of starting from random, we're going to use a simple heuristic system, like the Selinger system, to bootstrap our policy. And the way that we do that is with the sample workload. So initially, the user provides a sample workload. We see how the expert query optimizer works on that sample workload. And then we train our value network initially to model that expert. So how well does this actually work? We did a few experiments. These are experiments on the join order benchmark, on the Postgres database system, and we've normalized the latency here. So on this graph, that line at 1 is the performance of Postgres. So if we look at how long Neo takes per iteration, and an iteration here represents 100 queries, we can see that initially we do pretty badly. We do 2.2 times worse than the Postgres optimizer on iteration 0. So this is just after pre-training to try to match that simple primitive optimizer. We pre-train to match that simple optimizer. We do 2.2 times worse than Postgres. Not great. But pretty quickly, after about 10 iterations, around 1,000 queries, we've learned to match the performance of the Postgres optimizer. And then as time goes on, we can actually start to beat it quite significantly. So after about 20 iterations, which is around 24 hours of actual real time, on our test queries, we were outperforming the Postgres optimizer by 15 to 25%. But we all know that the Postgres optimizer isn't the most sophisticated in the world. So we also compared against the Oracle query optimizer. So in this graph, 1 represents the performance of the Oracle query optimizer. So we've renormalized everything. And the first line that I want to plot is the performance of the Postgres plans when executed on the Oracle engine. So this is just sort of a comparison showing if I take what PostgreSQL says I should do, if I take that query plan and I run it on the Oracle engine, how fast is it compared to Oracle? So it's approximately 70% slower, right? That's what that 1.7 means. Neo, on the other hand, tends to do a pretty good job. So again, initially, we start out pretty badly. With Postgres, we started out 2.2 times worse. With Oracle, we start out around, that graph is cut off. That's really bad. It's so that should be around 3.2, around 3.2 times worse than the Oracle optimizer. But then very, very quickly, we get down to just 2 times worse. And then soon after, this time around 40 iterations, which represents about 48 hours of training, we start to outperform the Oracle optimizer as well. This is really cool because the Oracle optimizer, it costs $5 million a year to maintain. It's an expensive piece of software. And if machine learning techniques have the ability to bring down the performance even more, or even match the performance, those 45 to 55 employees can spend their time doing something more productive than tweaking a query optimizer, right? They can build actual systems, they can work on applications, they can make things actually work instead of spending time fixing bugs in a query optimizer. We also looked at did a per query analysis of how these various operations worked. So here 0 represents the latency of Postgres, and a negative number means that Neo saved that much time, and a positive number means that Neo regressed by that much time. So look at the purple bars first. Those purple bars show you the main system that we've been talking about. So for example, on query 16b, compared to Postgres, we're saving almost 45 seconds of execution on that particular query. Whereas on query 24a, we're regressing by about 10 seconds, meaning that we're taking 10 seconds longer than Postgres to execute that query. So if you're a DBA and you're looking at this graph, you might think, okay, you're improving my mean performance a lot, but you're also regressing a lot of my queries. That might not be good. So these purple lines represent training Neo with what we call the workload cost. This is if you tell Neo, hey, just minimize the latency. Just make the latency as low as you possibly can. This is what you end up getting. Now, if instead you tell Neo, instead of minimizing the latency, minimize the ratio of the latency you achieve to the Postgres latency. So in other words, if Postgres achieves 10 seconds and you achieve 5 seconds, that's a reward of 0.5. That's a reward of 2. If Postgres takes 10 seconds and you take 20 seconds, that's a reward of 0.5. So with the workload cost, the purple, we're only looking at absolute latency. With the green bar, the relative cost, we're looking at the ratio of performance. If we train Neo to minimize that, what we see is our gains are a lot smaller. For example, on 16b, we only save 15 seconds instead of saving 45 seconds. But because we're optimizing for this relative score, we see way, way, way fewer regressions. And in fact, there's a couple bars, you can hardly see them, but there's only 4 queries that regress when we use this relative cost function. So another advantage of learned query optimizers is that you can swap out these cost functions at will. If you want to minimize total latency, you can do that just by plugging it in. If you want to minimize latency relative to a particular benchmark, you can plug that in as well. If you want to minimize memory footprint, that's fine. All you have to do is measure the memory footprint. If you can minimize disk I/O, anything that you want, any cost function that you can imagine that you can measure, you can integrate into this system much more easily than you could in a traditional query optimizer. So I just want to conclude by sort of highlighting and talking about some of the limitations here. So we do think that Neo is the first learned end-to-end query optimizer. We think that it uses tree convolution, which is a solid inductive bias for understanding how deep neural networks can learn functions about query optimization. We've shown that Neo can achieve performance on par with state-of-the-art commercial query optimizers, but there are a number of limitations, important limitations. The first one is that we have a dependency on this expert system, right? In order to not start out with a random policy, which would take, hours or even days to execute, we have to rely on a traditional query optimizer, albeit a very simple one. The second biggest problem with Neo is that our featurization, our scheme, requires the schema to remain fixed, which means that, no adding new tables, no modifying the schema of current columns, none of that. Obviously, this is a huge limitation, right? Because schemas change all the time, and you don't want to have to retrain your entire query optimizer every time you modify your schema. The other kind of more subtle issue is concurrent queries. So before we were using the query's latency as our reward function, right? We were saying, okay, this query ran, it had a latency of 5 seconds, try to minimize that. If you have 2 queries running at once, it's possible that you can run the same query plan twice and get 2 different latencies because of contention, right? So if I run a query plan one time and that query plan is really, really good, it's the best query plan I could have possibly picked, it might run in 2 seconds. But then later, I might run that same really, really good query plan in an environment that's much more contested, and it might take 20 seconds. Neo will see that change. We'll see, oh crap, this went from 2 seconds to 20 seconds, and it will assume there's something wrong with the query plan. I have to adjust it, I have to change it. This can lead to some weird instabilities. So these are big limitations and things that we definitely want to look at in the future. Just to sort of give a brief spoiler and to advertise our upcoming work, we've started looking at what we're calling BOW, which is a bandit optimizer. The idea is that while current query optimizers aren't great at finding the absolute best plan, at finding like the #1 top plan that you could possibly execute, current query optimizers are very, very good at avoiding plans that are absolutely terrible, right? So the idea behind BOW is, can we take a whole bunch of very simple query optimizers and learn how to stitch them together in a way that gives us better and better plans? So here on the right, I have a simple chart showing that the time elapsed versus queries finished in a 100,000 query workload. And in this case, Neo takes quite a long time to train, but BOW trains significantly faster. We have a preprint of this available if you're interested in taking a look. It's still pretty preliminary. We're still trying to work out the kinks, but it's available at that link there. That's all for the lecture portion. I'd love to take questions and start a discussion. I know that there was a lot of ML jargon thrown in there. I'm happy to go back over and try to make it a little more intuitive. You can grab these slides at that link. And yeah, that's my info if you want to find me on Twitter or the web.
Ryan, thank you for the talk. It was really awesome and refreshing, and you presented everything also with a critical eye, which was great. At this point, I would like to let people ask questions. I have a few questions myself, actually, but I will keep them last. So, guys, this is the right time to ask any of the things that you had in mind. Don't be shy.
Hello, I have a question.
Hi.
Can you hear me?
Yes.
Hello, Ryan. Thank you for the amazing lecture. I would like to ask, in a commercial databases, is Neo adapted in a large scale, or is it now in a research stage?
So it's okay. So I have to answer this question a little cautiously for political reasons. The short story is, yeah, it's still definitely in the research phase. There's still a lot of limitations on Neo that prevent it from going into like a full-scale production. The fixed schema is probably the biggest one. Like, I'm sure you can imagine Oracle's customers would be quite upset if Oracle said, oh, by the way, if you add a new table,
of course,
you got to wait 3 hours. But we're working with a few of the commercial vendors to try to integrate some of these approaches in a more limited way into modern databases. So BOW, our new work, is sort of moving in that direction. So the motivation for BOW is basically, how can we take Neo and make it practical for a database today? So yes, hopefully we will have a beta of that available for Postgres in the open source soon. But in terms of commercial adoption, yeah, it's probably still a couple years out.
Okay, thank you very much.
Hello, I would also like to ask something. Can you hear me?
Yes.
Does Neo need to be retrained from time to time? For instance, if the data changes in a significant way, do we need to retrain?
That's a great question. So there are a couple of things that can trigger the need for Neo to be retrained. One of them, like we talked about, is a schema change. A data shift depends on the representation that you're using. So I didn't talk about it here, but we talked about briefly about replacing histograms with learned embeddings. So Neo has if Neo is using those learned embeddings, then Neo can handle changes to the data, even pretty drastic ones, but you have to keep those embeddings updated. The details about that are in their paper, but it's reasonably easy to do. So just to directly answer your question, if you change the data in a drastic way, you have to retrain something. We have a shortcut with Neo, where if your data changes in a drastic way and you know, like you're aware, like you just did a big bulk load, you can retrain these embeddings, which is a very, very fast process, and then Neo will get up to speed. One of the things that's actually much harder for Neo to deal with is if your data changes in a drastic way, but it does it in a long period of time. So like over the course of a week, you slowly insert more rows and the distribution starts shifting a little bit. We don't really know how to detect or capture that yet. And if that happens, eventually Neo's performance will get really, really bad, and you'll basically have to start over. You'll have to say like, oh, okay, it's regressed. We have to retrain. So yeah, in some cases, if there's a drastic shift and you know the drastic shift happened and you can tell Neo, hey, the data just changed a bunch, you can do a really, really fast retraining where you just retrain the embeddings. But if you don't have that condition, then yeah, the Neo's performance will regress as your data changes.
Okay, thank you.
So can I ask something?
Yes.
So if Neo starts the training, while it trains, can the SQL server perform any queries, or does the training have to complete first?
So there's two. So yes and no is the answer. There's two phases to Neo's training. Oops, did I miss it? So in the first phase, you're modeling an expert optimizer initially. This is the learning from demonstration portion. You're looking at like what a simple Salinger algorithm does while on a sample workload. During this phase, no query optimization can happen. So you need to do this offline once while the database is not running any queries. Obviously, you could like run this on a different machine than your database or something like that. In the second phase, where we're using this feedback loop, where we're getting information about execution, when this training happens, you can absolutely keep executing queries. So do you need to stop query optimization in order to do training? Yes, for the initial training, but in the runtime loop, you do not.
Okay, thank you.
Can I ask a question as well?
Yes, go for it, please.
Thank you. I wanted to ask a very, I believe, basic question. I don't know. This system, NEO, and the reinforcement learning process, etc. I want to understand what system was it implemented in. For example, was TensorFlow used, PyTorch, something like that? That's my question, basically.
Sure. So I don't know if we joke a lot. We use a term called researchware, which basically means like a horrible hack that only works on my laptop. But the NEO system was implemented using PyTorch to run the tree convolution operations, the PostgreSQL database for modeling a simple query optimizer, and a couple of other intermediary Python tools as well, like pickle package, NumPy, Pandas, that kind of thing. But yes, the like primary framework for doing the actual reinforcement learning, the actual inference, was PyTorch.
Let me ask a question since I can grab this opportunity. So Ryan, since we are looking at this architecture here and following up on the previous question, so during the first phase, you will use the cost from the optimizer, and during the second phase, you're actually looking at the real execution cost as the real execution time, or something different happens?
No, that's exactly right. Yeah. In the first phase, we assume the cost model is correct. And in the second phase, we measure actual runtimes. Yeah.
Okay, and as long as we are here, so can you tell us now exactly what are the inputs for each of these modules?
Yeah, sure.
You say sample workload and user query, but what do we exactly have there?
Right. So the user query, the queue there is more or less a SQL query. Specifically, it's like a parsed form of it. So like you can think of it like the join graph kind of. The featureizer takes in that join graph and turns it into turns each node of the join graph into like a structured representation. So like we record stuff like what relation is it, what is where we find our embedded cardinality estimate, for example, if that's necessary, and we embed like where the predicates are, right? Like, is there a predicate on column 1? Is there a predicate on column 2? Is there a predicate on column 3? That kind of thing. Then for the value model in the plan search, the inputs and the outputs are partial query plan trees. So the value model takes in a partial query plan and it outputs just a single number, how good it thinks it is. And the plan search module takes in that single number prediction and then produces another partial query plan. And the experience just holds histories of this query plan took this long.
I see. So you don't use any query to vec or anything like that?
No, nothing fancy. So those kind of things. So we did some experiments with exactly query to vec, and found that it gave pretty good performance. It didn't actually improve the final policy, like like the performance after 100 hours was the same if we added in query to vec, but it did actually train quite a bit faster. We just thought it was like a little too much for one paper to also throw that in. But yeah, that featureizer module, you could do way more there than what we're doing. We tried to keep it really basic just to show that like you don't need something fancy in order to just make it work. But yeah, if you have stuff like query to vec or even histogram embeddings, like simpler stuff too, you get a lot of benefit. Yeah.
Any other question from the audience?
I have a question, if you can hear me.
Yep, go ahead.
What happens in the event of a crash if Neo, for instance, crashes? Does it have any checkpoints, or do we have to start all over again?
That's a great question. So like, what's the recovery mechanism for the optimizer, right? Because most query optimizers are stateless, right? They don't have to store data between query runs. So in a traditional query optimizer, if your database crashes, when your database comes back up, you're stateless. There's nothing to recover. So what we do in Neo, the only non-stateless component is that experience set, which is your past history of collected query plans and latencies. So what we do is we actually just store those inside the database itself. So we create a very, very simple table just with 2 columns, one column for the query plan as JSON and another column for the latency. I know it's violating first normal form, but it's okay. And then if there's a crash, that experience is preserved automatically by the database's own recovery processes. When the database comes back up, the only additional recovery step that we need is to train a new neural network on that experience, which is if you already have the experience, is a pretty fast process, like just a couple minutes. So I guess to directly answer your question, how do we do recovery? The answer is we store the experience in the database itself, and we rely on the database to do the recovery.
Okay, thanks.
More realistically, we just hope it never crashes.
So you mentioned that one of the assumptions in the current design of NEO is that you don't have a distributed environment, and well, you don't have concurrent queries essentially, because that changes a lot of things. So what is your take with respect to how NEO version 3.0 could it work on a distributed environment? How challenging is it?
Yeah, so there's a couple thoughts that we've had on this. So one of them is that in order to get a query to work on a query optimizer for a distributed environment, you really just have to think of it as some new operators that you have, right? Like you have an operator called like a network partition that says, okay, this is going to get executed on one node, and then the results are going to get sent over the wire, right? So in that sort of primitive system, it's pretty easy to integrate where do you put those network partitions into the MDP. But in reality, there's a lot more constraints than that, right? So like NEO, for example, it's able to build any binary tree that it wants. But in a distributed system, you might have some relations that are only on node A and some relations that are only on node B, which might really restrict the query plans that you could build, right? So NEO might produce a query plan that's not actually valid for your system, like in the sense that it might say, okay, do a local join of relation A and relation B, but A and B aren't actually on the same node anywhere. So there's some deeper thinking has to go into how to redesign the MDP a little bit in order to handle those distributed systems. Luckily, the problem of concurrent queries is a lot easier to solve. The simplest solution to solving concurrent queries is instead of using the wall clock time as your reward, you just use the CPU time, right? Which is pretty consistent regardless of the number of concurrent queries that are running. Now, that might not actually be what you want to optimize, but it's generally a pretty good proxy, right? Like if it query uses less CPU time, that's normally good. But yeah, so, right, again, to directly answer the question, to figure out how to make it non-distributed, the primary barrier is figuring out how do we represent distributed query processing as an MDP. And in terms of concurrent queries, the primary concern is how do we measure how well we did, right? Like if you execute a concurrent query, what's the signal that tells you if you did a good job or a bad job?
Mm-hmm. And just to follow up, what happens when your query workload changes? George earlier mentioned about what happens when data changes. But what happens when the query workload changes a lot? And we see that in different environments, right?
Right. So that is a great question. So the first thing I'm going to do is I'm going to pitch our next work again. So BAO is built around the idea of let's figure out how to handle dynamic schema, dynamic workloads, and dynamic data. So we have new techniques to handle all three of those things and new experiments to go along with it. But for NEO, how do we handle dynamic workloads? Well, if your workload changes gradually, slowly over time, all is well. The reinforcement learning algorithm will automatically learn how to adjust to that distribution gradually, and it'll figure it out just from the reward signal itself. So we have an experiment in the paper where we start out a query workload from one set of templates and then slowly transition it to another set of templates. And indeed, NEO learns to smoothly follow that. Now, if your query workload changes drastically all at once, like you go from running these 10 templates and then the next minute you're running a totally new set of 10 templates, NEO's performance will regress a ton. So immediately when you do that switch, when you have that drastic change in your workload, NEO will go from doing, 85%, 75% of Postgres's latency to doing like 1.5 or 2x worse again. It'll learn a little faster, like the curve will come down a bit more quickly. Yeah, overall it can definitely be a problem. Actually, I think I might, let me see if I can. That shows exactly this. Oh man, can never find it. Crud. It's only in the archive paper. All right, yep. Unfortunately, I don't have it, but happy to send you that graph. But yes, basically what happens is if your workload changes gradually over time, everything's fine. If it changes drastically all at once, there's a massive regression. Yeah, because Neo has basically learned to expect a certain workload.
Right, right, that makes sense. Any more questions? Okay, if there are no more questions, then Ryan, do you have any questions for us? You can, you know, you can also ask questions or tease the students.
Oh yeah. See, you're all an undergrad class at Athens, right?
They are master. It's a master
okay.
on data science. Yeah.
Oh, okay, very cool. So what's the end goal of the course? Is there a big project or like a final exam or?
Actually, today after this lecture, we are going to discuss about the final project assignments, and we are having you know, a few topics. So if you have ideas, last year actually one of the people that are attending this call and hasn't asked the question, I'm looking at you, number X, I did a good effort to, you know, implement Neo at some part of it at least, and it was a great experience actually. We enjoyed it a lot.
Good. I feel for you trying to implement Neo, whoever that individual was. There are a lot of hyperparameters and things to tune.
Yeah, sure.
Yeah. Yes, I would challenge all of you when you're doing your final projects to try to think, is there a simple and clear way that I could use a very simple machine learning technique to make this a little better? I think that you'll notice that computers are getting more and more complex very quickly, especially when you look at the cloud, right? Like there are so many different virtual machine types. There are so many different configurations and instances, so many different options. And the complexity is growing way, way faster than our human capability to keep up. Like we can only fit so much stuff in our brains at once. You know, 4 years ago, 3 years into my PhD, I would have said, oh yeah, I'm an expert on AWS. I know what most of the services are. I know what most of the virtual machine types are. I know what the trade-offs are. Now, if I look at it, no way. You'd have to spend 5 years learning that stuff just to truly understand it all. So I think because of that, because systems are getting more and more complex, because our human capacities are growing slower than the complexity of the systems, these machine learning models are really important, right? Figuring out how to make a system that can automatically adapt to new hardware, new configurations, or figuring out how to make a system that can invent new strategies for itself, or even figuring out how to more clearly express our intention, right? More clearly express to a system what I want to do. I think all three of those tasks can be aided by machine learning. So yes, I guess my challenge to everyone is it doesn't have to be super complicated. It doesn't have to be deep reinforcement learning. In fact, the simpler it is, the higher the likelihood it works. I would challenge you all to think about that, because I think it will really, really separate the people who can get the most out of computing resources in the future from people who are still sort of stuck in a traditional model. That's all opinion. Yeah.
But of course you did reinforcement learning, right?
Yeah.
So if one would ask you, you know, I want to have my project on something cool, what would you suggest as you know, final project assignment that someone could work on for the next few months?
So I don't know if it'll exactly fit into the scope of the class or not, but one thing that might be really interesting is if you look at the Postgres optimizer, there's wide classes of errors that it will make. So if you download the join order benchmark, which is from the TU Munich folks, there's a whole lot of queries in there where the Postgres will make this mistake. It will make this mistake where it will use a nested loop join where it really shouldn't. Basically, there'll be an underestimate in the cardinality estimator, and that will cause Postgres to think, this join is really tiny. I'll use a nested loop instead of a hash or a merge, and that will cause a big old slowdown in the query. Now, you can tell Postgres, hey, on this query, don't use a nested loop. And on those queries, if you tell Postgres don't use a nested loop join, you can get like a 10x improvement. Unfortunately, on other queries, if you say don't use a nested loop join, you get a massive regression. So a simple project that might be interesting is trying to make a machine learning, a very simple classification system that decides, okay, for this Postgres query, should I use a nested loop join or should I disable nested loop join? Again, I don't know if that'll fit with the scope of the class, but I think that would be tackleable in a couple months.
Yeah, that sounds actually very interesting. And maybe, if someone is interested in doing this, maybe they can contact you and ask for feedback or, questions or anything.
Yeah, absolutely. We're always willing to help. We're always looking for collaborators if you really want to turn your project into something broader later. Yes, absolutely. My email address is that's on these slides, but I guess I should put the links up again. And if you think of anything else, if you think of any other clever ways you might want to apply machine learning to a database system, we're always open ears.
That is great. That's great. Any questions? Any other questions as we are approaching 7 o'clock here?
If you have any advice for us, the upcoming scientists, any advice for beginning?
Yeah, I might be a little too. I'm still kind of an upcoming scientist too. I guess my advice would be try to, as best you can, actually learn the theory behind things. Like it's very easy with these machine learning techniques to pick up a toolkit like scikit-learn or, Keras and just stitch stuff together and throw models at the wall and kind of see what sticks. And doing that won't, like you can solve a lot of problems that way, but you won't really understand your solutions and you won't understand their edge cases and you won't understand their failure modes. So I think taking the time to just pick a few statistical techniques, even simple ones like linear regression and random forest, and try to deeply understand them could be really, really valuable to scientists going forward.
Thank you very much.
So can I ask something?
Yes, go for
Do you hear me?
Oh, yep, I hear you.
Yeah. I want to ask, have you tried using machine learning techniques to improve the order of the queries that will be executed in a database server to reduce the total latency?
That is a great question.
Predict which one is going to take more time and less time and make it more real time.
Yeah, that is an awesome question. So just to expand on that a bit, oftentimes when you're executing queries on a server, you might have an SLA, you might have different performance goals, right? You might say, okay, I need these queries done fast, I need these queries done slowly, or you might just be trying to do something as simple as minimizing the average query latency, right? And then choosing which query to admit next